Hi, in this video we are going to talk about the first strongly connected component algorithm, the so-called Kosaraju algorithm. So let's get started. Basically we have to use a stack for depth first search traversal because we have to track the finishing times. And we need to track whether we have already visited a given node or not. So first we have to do a depth first search on the original graph and keep pushing the nodes to the stack. Then we have to transpose the graph, which means that we have to reverse the edges. And then we keep popping the nodes from the stack and keep constructing the strongly connected components one by one. So we have this graph with 8 vertices and lots of directed edges. And we have to use a visited set to track whether we have visited the given vertices or not, and a stack abstract data type. So let's start at a random vertex. I started from the vertex A. Okay, we add it to the visited set because we have already visited it. Then let's visit its neighbors in a depth first search manner. So we visit the C and we add it to the visited set. Then we visit all of its neighbors in a depth first manner. For example, we keep visiting the right child, which is the E, and we add it to the visited set. Then we visit the neighbors of the E. So for example, it has 2 neighbors, the G and the F, but we visit its neighbors in a depth first manner starting at G, and of course we have to add it to the visited set. Then we visit all the neighbors of the G. One neighbor is the E, but we have already visited the vertex C, so we keep going to the edge, and of course we add it to the visited set. We visit all the neighbors of the edge. We have already visited G, so we keep going to vertex F. Okay. Then we visit the neighbors of vertex F, which is the vertex D. We add it to the visited set. And now we come to the conclusion that, okay, the D has a single neighbor, the vertex F, but we have already visited it. So we come to the conclusion that we have already visited all the neighbors of D. So basically we add it to the stack finally. And we keep backtracking. We backtrack to F. We come to the conclusion that we have already visited all the neighbors of F. So we add it to the stack and backtrack to the previous node, which is the edge. For vertex H, we have visited all its neighbors, so we add it to the stack and backtrack to the previous vertex, which is the vertex G. We come to the conclusion that we have visited all the neighbors of G, so we add it to the stack and keep backtracking to the vertex E. Again, all the neighbors are visited, so we push it to the stack and keep backtracking. What about the C? The C has 3 neighbors, the vertex B, the vertex D, and the vertex E. We have already visited all of its neighbors except for the vertex B. So it's very important that this time we are not going to push it to the stack. We keep visiting its neighbors in a depth first manner, so that's why we add the vertex B to the visited set. And keep visiting the B. We come to the conclusion that the B has 2 neighbors, the vertex A and the vertex D. We have already visited both of them, so we consider the vertex B to be done and add it to the stack, and we backtrack. So the previous vertex is the C. We come to the conclusion that all the neighbors are visited, so we are done with vertex C, so push it to the stack and keep backtracking. Because we come from the vertex A, we go to vertex A, come to the conclusion that we have considered all of its neighbors, so we push it to the stack and consider it done. So basically all the vertices has been pushed to the stack, so it's time to construct the so-called transposed graph. What does it mean? We have been discussing that we just have to reverse all the edges in the original graph, and this is exactly what's happened here. We are going to pop the items out of the stack until the stack is not empty. So basically the algorithm is going to iterate as far the stack is not empty, and this is how we are able to find all the strongly connected components. So we pop the first item out of the stack, which is the vertex A, and of course we considered it to be visited. And we keep visiting all of its neighbors. So we go to B and we push it to the visited set. Then we visit all the neighbors of vertex B, which is the C basically. We haven't visited it, so we add it to the visited set. And we visit the neighbors of C, which is basically the vertex A. So we come to the conclusion that this is the first strongly connected component. So we start at the vertex that we have popped out of the stack, and until we are able to traverse this subgraph in a depth-first manner, so with the help of depth-first search, and basically this is the second depth-first search. That's why we have been discussing in the theoretical section that we have to do two depth-first searches. First on the original graph, and the second depth-first search on the transposed graph. Okay, so this is the first strongly connected component. Then let's pop another item out of the stack. It is the C, but we have already visited the C. Then we pop again. It is the B, but we have already visited the B. So we keep popping. This is the vertex E. Okay, so it's going to be the first item in the second strongly connected component. And we keep considering all of its unvisited neighbors. It's very important that we are not going to bother anymore with the visited vertices. So okay, it has two neighbors, the C and the G, but we have already considered the vertex C, so we keep visiting G, and it's going to be the second item in the strongly connected component. We visit all the neighbors of G, we have already considered the E, so we have the H. What about the neighbors of H? It is the G, but we have already considered G, so basically that's all about the second strongly connected component. Okay, so we keep popping items out of the stack again. The G has already been visited, the H is already been visited, so we pop the F. So it's going to be the first item of the third strongly connected component. We visit all of its neighbors, but we have already considered H. We have already considered vertex E. Okay, we have the vertex D that haven't been visited so far, so we visit it. It's going to be the second item in this strongly connected component, and we visit all of its neighbors. But we come to the conclusion that there are no unvisited vertices, so that's all about the third strongly connected component. So we keep popping the items from the stack. But we come to the conclusion that the D has already been visited, and this time the stack is empty, and we have to iterate, we have to run our algorithm as far as the stack is not empty. In this case, we come to the conclusion that it's over. We have managed to find all the three strongly connected components, so the algorithm terminates. So that's all about basically the Kosaraju algorithm. We have to do a single depth-first search on the original graph. Then we have to do another depth-first search on the transposed graph, and we have to use a visited set to be able to track whether we have visited a given vertex or not. And of course we have to use a stack in order to be able to construct the strongly connected components. Thanks for watching.